we're going to apply our process, our problem-solving process, to the situation where we have a finite length of one-dimensional charge. So this is a line of charge, and we want to find the electric field at this point. Now note that r here is a variable. We're not actually specifying that there's a specific point here at 10 centimeters. We're actually saying here that it's from the middle. So the first step is to not just draw the geometry here, but also start labeling your coordinates. So what is a good coordinate system to use in this situation? We're going to call this direction the y direction. We're going to call this direction the x direction. So we see that a good choice for x equals 0 is going to be the line of charge itself, and a good location for y equals 0 is going to be on our point, which is also halfway. So note that the distance up here is going to be y equals 2, and so that coordinate here is plus y equals 2. And at the bottom, which is slightly cut off, is L over 2. So be careful and make sure that you understand the geometry that you're working with. And again, these ideally should be labeled on your picture. Again, feel free to start a second picture if you realize that your first one is too small and you can't actually label everything. So the next thing to note is that we can say that there is a charge density. Now you might just be told that you have charge density lambda. A different option, which is what we're going to more use in this case, is that we have a total charge Q and a length L. And again, we're assuming that our object is uniformly charged. So in this case, we've started drawing a picture, but we haven't done very much yet. The next thing we want to do, we have our specific point here that we're going to think about. So we're assuming it's at distance r, which is going to be a variable. So in the end, we will actually have our electric field as a function of r. The next thing we want to do is select a tiny point which is going to represent our delta Q. So we have our delta Q, and you now want to say, okay, I have my delta Q. What is sort of electric field is that going to create here? Well, and this is where you can do a little bit better drawing with a ruler on paper than I can on my screen. But you get an electric field like that, right? It's pointing away. It is a vector. And if we call this point I here, then this is the electric field from point I. So now note that there's an angle here, theta, and that theta is going to depend on which Q value, delta Q, you picked. And that's important since when we do our integral, we're changing which value of delta Q. Again, I'm not starting with my integral, but I just know that that's where I'm ending up at the end. So I have my theta value, and note from geometry that this is also then theta. And the reason that that matters is you'll want to break this into components. If your picture is big enough, you can go ahead and label it here. I drew a new picture out to the side. We take our electric field vector and we're breaking it into the x and y components based on theta. And I really do encourage you to draw this picture. Now, obviously, you can then write out the trigonometry of what's happening, but you really should have it drawn as well. So this is the start. We then can actually start defining what this looks like, this electric field magnitude, based on Coulomb's law, the electric field from a point charge. But again, we have this theta to think about. The other thing we need to think about, and you might realize this when you go to actually use Coulomb's law, is that we need that distance. That distance here is not r, right? This distance is here. That's not what we have. We need to go from here down. That's going to be ri. Note that that is the hypotenuse of this triangle, right? So again, this is another triangle going on your picture, and because we need this quantity for actually writing it out. So I'm not even done yet, and you can see that this picture is getting fairly messy. So on the one hand, you might really want to use different colors, or feel free to actually draw multiple pictures so that you can just use pencil and erase it if you start making mistakes. So this is the example of what the book looks like, and the figure in the book. You can see that it's really similar to what I was doing, except one thing they did that's really helpful is actually show two different segments. note that these are equally positive y and negative y position. And so when we draw the electric field from each of these, it's equal in magnitude, but you actually have a slight difference in direction such that whatever y components you have, right? You have this EY component, oops, sorry. You have this EY component here, and you have an EY component here that cancel. So once you have that, you say, okay, I'm going to realize that I don't need to worry about my y components from each of these pieces because the y component of the electric field from each piece on top will cancel with a corresponding y component on the bottom. Now this is called using symmetry, and you should explicitly say that you're doing that, and it should be clear. So in this case, actually showing the y components, labeling them a little more clearly than I have here, and explaining that you're not going to worry about the y component because you see it cancels, that's necessary. If you just never calculate the y value, it isn't clear whether you forgot to do that or whether you knew that it canceled. So anytime that you get to say something is equal to 0, you need to show a clear justification of why that's the case. So then we're left with our x components, that again, the x components of the electric field, that again we see are going to need to depend on theta, since the magnitude goes into x and y based on theta, and this direction, this distance, which is again the hypotenuse of a triangle. Well, what are the sides of this triangle? This side is actually the y value of whatever piece you're talking about. This side is r, which again is a variable, but it's not a variable we're integrating over. It's, for the extent of this problem, a constant. So what that means is we can use Pythagoras' theorem to say that this is going to be square root of r squared plus y I squared. Now, why do I keep writing that little I as a subscript? Because this shows me that this is not a fixed value. This depends on which charge I'm talking about. So later on, just like theta sub I, I'm going to need to transform this before I do my integral. So any quantity that is not fixed for every single little point charge that you've broken your object into, use that subscript so that you remember later to actually break it up. So let's start doing some math. Again, this is a pretty good representation, though I would encourage you to also show the components explicitly. And the first thing to know is we get to use, again, the electric field from a point charge. Now here I'm showing that it's just the magnitude of it. Again, the direction is going to depend on this theta I. And 1 over 4 pi epsilon naught is our normal constant. The charge of this little segment is delta Q. It is not total Q, right? It's not the entire charge, it's just little delta Q. And later we'll need to transform that into a position. On the bottom then, our distance squared, but again, it's a specific distance that's related to which charge we're talking about. The next step is to say that, again, one thing you would have shown very clearly in your work is that we don't have to worry about the y components because they cancel due to symmetry, but we need to worry about the x components. So to get the x value, and again, you would have a triangle showing this out, is that it's going to be the magnitude of our field times cosine of theta. Now again, ideally, you would call this theta I to remember that you're going to need to actually keep track of that for your integral. Now, I've already said before that we get to say that the y components are equal to 0, and again, that's not that the individual ones are, but the sum of them are, and you should have some sort of work showing that or justifying that. So finally, when we want to set up our integral, we see that we're going to be integrating over y, right? We want a spatial coordinate. So in our integral, we're going to have dy show up. So we need to go back and get theta in terms of y. We need to get this r in terms of y. And previously I showed you how that could actually relate, especially this r value. So from geometry, we get that, again, Pythagorean theorem, which is why you should have really clear pictures with everything labeled, right? This geometry you should be able to just read off of your visual representation. Now the theta should also be coming from r and yi. So now this is a little trickier to see. So we have this side and we have this side. So this is our r, this is our yi, and you see a theta. Now you might be tempted to use the inverse tangent function, right? I can say arctan of this stuff equals theta. That means you're going to have an inverse tangent in your integral. Now ask yourself, do you remember how to integrate inverse tangent? Now you might, and that would be fine. I, for one, don't. So I would not want to put an inverse tangent in my integral unless I'm ready to integrate that. So there's actually something different we can do. So don't actually think about replacing theta, or again, specifically, this is going to be theta I, but think about replacing cosine of theta I, right? We have this whole cosine of theta up here. And again, if you try to do an inverse tangent for that, and then you have a cosine of that, that's going to be a nightmare. So just say that cosine of theta I is adjacent over hypotenuse. Your adjacent side is r, your hypotenuse we have from Pythagorean theorem. So be a little bit careful in that these angular replacements can get really into a nightmare if you don't think about planning them a little bit first. So we've now made those replacements. We've done a little bit of algebra, and this is our new component. So all we've done is we've gone from this, and we've actually really just looked at the x component only, and we've thought about breaking this distance up. So this looks a little messier, but now we have x component. We still have delta q. I haven't done that replacement yet. So we also now only have been talking about one individual piece, but we need to actually switch to a sum. We don't want the electric field from only one component, we want the electric field from all of them. So we're going to do a summation, and this is actually a middle step that you don't normally need to write down. I'm just explaining the process to you here. So we would be doing a summation, but you then say, well, how many pieces are there? And that will become an integral. So this middle piece you don't actually need to do. You just need to know that inherently that's what we're doing. We're going from one little piece, but now we're going to switch to an integral. So this is what our sum would look like, and when we write it as an integral, we actually need to change our delta q. Oops, this is the wrong thing here. That should just be r. So we have delta q. Sorry about this mistake. This isn't ri, this is just total r from our hypotenuse. So what do? We are going to change our delta q to actually be in terms of lambda, our charge per length, times delta L. Now in this problem, we're not explicitly going to show lambda, but you could if that was something given to you. And delta L in this case is the little length of this segment, but that's going to become delta y, and you know for doing the integral that delta y is just dy. So really all we're doing is moving from a charge here to a position that we can then integrate over. So again, forgive, that's the wrong thing here, but we then have dy, and it's okay that this is yi, right? Because now you just drop that and say, oh yes, I am integrating over y. So the only subscript that should be in your integral is on the same coordinate. So this was actually just a mistake that I made in writing these up. And this is actually then what you would have. Now you have to get the bounds on your integration right, and this is where the coordinate system is important. We're not integrating from 0 to L, we're integrating from negative L over 2 to positive L over 2, and that really is going to matter. Additionally, don't forget that we did acquire that R on top, and that came from geometry. Now you see that we had this Q over L, these are both fixed values, so we can actually pull those out front. So we now are left with an integral, and remember this is for the x component of the electric field. Since we have argued through symmetry that the y component 0, we do in fact get to say that this is your total electric field as well, that would be pointing in the x direction. So now you do that integral. And this is the result that you get. Now, again, here I'm going to call this a rod, which just means a finite length line. We have our normal constant out front, we have Q on top, where that's the total Q of the rod, and then on the bottom we have R, and then we have the square root of this stuff. So there's a couple of checks that we can do. You've done a lot of work, so you want to make sure that it's been correct. The first is whether or not the units are correct. So I've put in parentheses dimensions, because in this case you don't literally have units. Do not write units off to the side. Everything is inside the variables. So we can just ask whether the dimensions, i.e. the types of quantities, match our expectations. Now you might say that you have no idea what dimensions it should be, but remember, and we're not even going to worry about this constant out front right now, you know that for a point charge, the electric field is 1 over 4 pi epsilon naught, hey, we still have that, Q divided by R squared, distance squared. So really the question is the bottom like distance squared? We have a distance here, but then we have a square root of a distance squared plus a distance squared. So square root of distance squared is simply distance. So we have Q over distance times distance. So the dimensions are correct. I'm not talking about coulombs and meters because those things are hidden in the variables, but just in terms of time, length, mass, charge, distance, you can do the same thing. So the next question is whether this becomes a point charge if R goes to infinity. And what we would want to do in this case is say, okay, well, as R goes to infinity, what changes about this? Well, on the bottom, this term effectively becomes very small so that it's insignificant. And R times square root of R just becomes R squared. So yes, in fact, as you take R to infinity, this does become the electric field of a point charge that has charge Q, which is what we would expect. This is a finite line of charge, which we call a rod. So it is possible to get far enough away from it for it to look like a point charge. The next question would be, well, what if the length of this went to infinity, which is the same thing as saying, well, what if we're really, really close to it? And in this case, we don't know what to expect. I know it's not going to look like a point charge. So in fact, that's what we're going to do in the next video, is look at what do we get if we look at an infinite line of charge, which is what this becomes if we literally take the length to infinity, or if we just say that R is really, really small.